Okay, our next speaker is John Harding from the New Mexico State University, who is where he is currently the head of the department. Professor Harding is also the president of the International Quantum Structures Association from 2014 to 2016. So Professor Harding gave an interesting talk about set theory and quantum physics back in July at another conference. And so Professor Harding is going to give a talk on something that is maybe a little similar. So this would be convolution algebras. So without further ado, Professor Harding, please go ahead. You are muted. Professor Harding, you are muted.
Thank you very much for the nice introduction. And it's a pleasure to be here.
Thank you.
Is everything, you can hear me and you can see my slides now? And
yes.
Everything's wonderful with these online conferences, except we somehow have to figure out the fact that you're on the other side of the world from me. This is the last big problem for us. I don't know how we're going to fix this one, but so today I'd like to talk about something. I'll put it under the title of convolution algebras, and so it's a bit of a story of a topic that began in one place for one purpose and took a little bit of a path through other places. And I'd like to sort of give an overview of the trajectory of things rather than give too much detail about any particular piece of it. And this is work that I did with Carol and Albert Walker here in New Mexico. So I don't know how people feel about fuzzy things. Some people like them quite a bit. Some people don't like them very much at all. But if you're in the second category, don't be too alarmed here. It's this will go other places than fuzzy. And I should say at the outset that this is a talk in a logic society, and I'm not going to view fuzzy logic as a logic. That's not my purpose here. I'm agnostic about this thing. Fuzzy logic is a thing, and I want to study it. And the tools that will come out will have a logical flavor in the tools that I use. And so just like we were, just like you can study properties of numbers and constructibility with logical tools, you can study other things, and that's the view I take. So if I make the mistake of using something like a word that may have a technical meaning, like belief function or something like that, that's just an accident of speech. There's nothing loaded intended about that. It's a thing. So let me say just a little bit about fuzzy subsets of a set. So if you have an ordinary set, these are meant to be degrees, temperature degrees in Fahrenheit. Okay? So in Celsius, they're all quite hot, but in Fahrenheit, it's sort of a range of normal temperatures. A type 1 fuzzy subset of this is a map. I'll call the map cold, and it's mapped from this set to the real unit interval. And this is a perfectly well-defined thing. The way I can put words to it is it's an expert's opinion. I don't know that you need an expert for this, but that's what we'll call it. That 60 degrees Fahrenheit is cold is 0.8. So we ask somebody, give me a number between 0 and 1 that reflects that is your opinion of this statement that 60 degrees Fahrenheit is cold, and they give you 0.8. So there's nothing ambiguous about this. This is a very well-defined real process in the world that people use, and they build devices based on this. It exists. Yeah? And so it's just a certain function. That's a type 1 fuzzy subset of X. Now, if you were asked such a thing, you would say, I find it rather hard to pick a number. Like, why do I pick 0.8 instead of 0.752 to reflect my opinion of this? It's a bit, you know, you get what I mean without going into detail. You can ask you can allow the expert to, instead of giving you a number, to give you an interval. 60 degrees is cold. Well, the expert says, well, it's somewhere between 0.6 and 0.9. I'm happy with that. This is called an interval valued fuzzy subset of X. And so it's, again, a map from X to the set of all ordered pairs from 0 to 1, where the first coordinate's less than or equal to second. Open interval, closed interval, I don't know. It doesn't, well, this is the actual definition. Now, if you, I don't know the background of people here, if you have a bit of order theory in your background, you may already start noticing this as there's a construction called twoing of a distributive lattice to get a De Morgan algebra. And you may already notice this existing in here. We'll come back to this. Now, a type 2 fuzzy subset, which is what we want to talk about here, we allow a different kind of thing. So instead of the expert giving you a single real number or an interval, they're allowed to give you this sort of, don't take it too technically here, a distribution. I don't really mean it in a technical sense. They're allowed to give you a function from 0 to 1 to 0, 1. They're allowed to sketch this to say, I think it's probably, you know, here's their opinion. It's a more flexible kind of thing. There are other ways to think of this. You could aggregate it over a bunch of people, all kinds of things like that. That's a type 2 fuzzy subset of X. Well, is this clear? Each one of these things is one of these functions. It's actually a fuzzy subset of 0, 1. Right? Now, truth value algebras. So the truth value algebras for these three things, fuzzy sets, interval valued fuzzy sets, and type 2 fuzzy sets. I should really be saying fuzzy subsets, but it's this is common. So the truth value algebra for fuzzy sets is just the real unit interval. The truth value algebra for interval valued fuzzy sets is this. It's all the pairs where A is less than or equal to B. It's all the intervals. The truth value algebra for type 2 fuzzy sets is all these functions from I to I, right? So in other words, I to the I. Both of these two sit in here, right? This sits in here and this sits in here. Each single real number is a degenerate interval, consistent where A and B are the same. And each interval can be realized as its characteristic function. So this is increasing levels of generality. I and I2 have naturally defined operations, meet, join. Neat in I is just infimum. Join is supremum. This operation star is a type of negation. And what is the negation of a number between 0 and 1? Well, the negation of 4/5 is 1/5. It's 1 minus. It's an order inverting operation of period 2. This also has an order, well, this also has these same types of operations, has a meet and a join, they're component-wise. To flip around an interval, you have to, it's not component-wise anymore, or it wouldn't be an interval. You have to flip around the components to keep things going well, and so forth. But these become De Morgan algebras, which are very nice logical structures. Now, Zadeh in 75 had defined the following operations on M, which are the functions from I to I. He had meet, a join, an involution, a 0, and a 1. And they're quite unusual definitions when you look at them. And when I first saw them, I thought, ew. And but at the end of all this, I come away with the impression that, that was remarkably insightful of Zadeh to have done this. I don't know what his motivation was exactly, but it's really quite lovely. Let's start. So when you look at them, you see that it's quite a unpleasant thing involving an infinite join of, well, we take the values of f at y and at g at z, where the mean of these two is this. What a terrible thing. If you try computing with this, you'll see how unpleasant it is. So, I mean, you can ask for all kinds of properties of these things. Are these, is this an associative operation? You know, have fun. Okay, it's really not so enjoyable when you sit down to do this. And there's a practical thing of you may actually want to compute with this if you want to work with type 2 fuzzy sets, and people do. So let's start pulling apart what this is. These operations, they all have the same form. It is not so clear down here because they're too simple, but you see it better up here. They're a join of meets, a join of meets, a join of, well, one thing is a meet of just one thing, so it's okay. Here you're actually taking meets of nothing. So it gets a little bit funny to think about, but it's just too simple. Where do the operations actually come from? Well, here you see that this guy is what the join is taken over. We're using the meets that turn to x. Here we're taking the joins that go to x. Here we're taking the things that whose negations are x. And here you can write them down, but they're too simple. It's so these are what are known as convolutions. So the easiest, there's a couple of easy examples of convolution. I'll do this one. Polynomial multiplication is a convolution. Here P and Q are polynomials, and by P, so this is ordinary multiplication of polynomials. What's the coefficient of x to the n in the multiplication of these? It's the sum of the coefficient of the I of x to the I in P and x to the j in Q, where I plus j is n. This is a convolution operator. Here they also occur in analysis quite a bit, and it's the same kind of thing as what we're doing here. So these funny operations are actually convolutions of the operations that exist on I. The meet, the join, the negation, the 0, and the 1 on I. So we're convoluting operations on I to get these operations. And so let's start taking a look at deeper properties of these things. Now, it turns out that M is I to the I. It's this type 2 fuzzy truth value algebra. It satisfies all the equations for a De Morgan algebra, except a regular absorption for lattices, which is x meet, x join y is x. And similarly with join, that doesn't hold, but you do get this. And the distributive law, it doesn't hold, but it's sort of weakened version, this does. This is sort of these are balanced versions of those identities. And there's something about that these equations have to be balanced, but I won't go into that. This M that you get is not a lattice because absorption doesn't hold. The unbalanced distributive laws don't hold. And M is a type of thing that's been known before. It's called a De Morgan-Birkhoff system. These Birkhoff systems came about quite a long time ago in Birkhoff's lattice theory book. I probably the first edition. So this is probably in the 40s that these things were introduced. Later, we'll return and to see why these things are true. I mean, have fun verifying these from the definitions. It's not an enjoyable kind of thing. You can probably do it if you're persistent, but you won't be having a happy day. Now, let's turn for a minute to a related algebra. So a function from I to I, so an element of M, we'll call it convex normal. So please beware that these terms are standard terms, but they were introduced by engineers working in fuzzy theory. Convex probably doesn't have the same meaning that you would expect for convex. Okay, so there's a reason for it, and you can justify it. But let me not go down that path. So realize that these words were introduced by people who work by engineers unfamiliar with other meanings of them, and just take it for what it is right here. It's convex normal if it goes up to 1 and then goes down. So in other words, it never goes down then up. And it doesn't have to actually attain 1. It just has to be the supremum of the values and things like that. But these details don't matter too much for us right now. It basically goes up and down and it takes value 1. These aren't a bad restriction if you think of the intent for which these type 2 fuzzy sets are meant, right? To express what do you think of 60 being cold? It's unlikely you're going to have a bimodal distribution, right? It's not impossible. You can conceive of situations, but these certainly are the ones you would most naturally think about. Now, it turns out you can do a very nice thing. These convex ones, I can take where it hits 1 and I can reflect it in this line, and it works out to be something like this. And I'll call this straightening, okay? It turns out that when you straighten this guy, you wind up with a decreasing function from the real unit interval to 0, 2. And this straightened version, it takes the convolution operations on these things. It's not clear that the convolution operations, these things, when applied to convex normal functions, give you a convex normal function, but they do, is when you apply these convolution operations, they just turn into pointwise meet and join. So that certainly gets the mystery out of what's going on, at least in the convex normal setting. And it turns out that these convex normal functions are a subalgebra of M. And if you take the quotient of this subalgebra modulo agreement convexly almost everywhere, so I say that 2 convex normal functions agree convexly normal almost everywhere. If when you flip them, when you straighten them, they agree almost everywhere in the usual sense in real analysis. Okay? This winds up being an actually absolutely lovely lattice. It's completely distributive De Morgan algebra. It has a natural compact Hausdorff topology under which the operations are continuous, and you have a metric on it. So it's evaluation into the reals. And so this is absolutely a beautiful order theoretic thing. I think that something I'd like to do sometime is this should have a natural axiomatic characterization, but I don't know what it is, but that would be an interesting thing to do. It's beautiful lattice. So from these unusual operations that Zade had, you get an absolutely fantastic kind of thing. You can extend this further. I don't want to go too much into fuzzy theory, but if you have if you know a bit, if you have something called a t-norm, the convolution of any continuous t-norm on I, you can convolute a t-norm the same way that you convolute these other operations. If you convolute a t-norm, you get a commutative quantile structure like this. So you get quite interesting order theoretic structures that naturally occur in lots of kinds of studies related to logic. That's sort of what I meant by the tools that we'll use to study M are logical in nature. Okay. Now, that's sort of the first part of the story. Let me shift gears a little bit. And we began in a practical place with this truth value algebra M for type 2 fuzzy sets. We sort of vaguely tied this to convolutions. We said, okay, this looks like what you do with polynomial multiplication. And let's return to convolutions, but in a more deliberate way. And I don't mean to say that this is the only way that you can talk about convolutions. Indeed, there's other ways you can talk about them, but I want to start making things quite specific in one direction. And look at that. I'm going to take a relational structure. It'll always be with this symbol, sort of fancy X. What that is, it's an ordinary set with a family, an index family of relations on this set. So this could be a binary relation on X. So in other words, a subset of X times X, or it could be a ternary relation on X, subset of X times X times X. Okay? So it's a set with a bunch of relations on it. Now, an important note is this is quite a general thing. A binary operation on a set, which is a function from X times X to X, is really a ternary relation on X. The ternary relation being all pairs A, B, C, where A plus B equals C. So this type of thing is actually quite a general setting. It's more general than algebras. It's more general than groups and rings and so forth, right? So it's a very general kind of thing. And if you have a logic, a certain type of logic background, you know that relational structures are a real ingredient in many paths in logic, right? And well, maybe I'll get to that in a minute. Here, let me first do this, and then I'll come back to that thought in a minute. So I want to take a relational structure X. So here I'm going to talk about convolution in a little bit more detail. And I'm going to take also a complete lattice L. That's a new ingredient for us. Well, let me make it a little bit more specific when we're going through it. Where are we? So here, when I'm talking about M, I've got two things. I've got two copies of I. One of them has an order structure, which is a complete lattice, and the other has an algebraic structure. Let me go back to here. Sorry to jump around a little bit. But I've got a relational structure and a complete lattice. From these, I'm going to make something called a convolution algebra. So what it is it's the complete lattice, L to the X. So this is just the X to the power of L, right? The product of L, X times with itself. That's a complete lattice. These are all functions from X to L. But now I want to define operations on this structure through the relational structure of X. And I'm going to define these operations by a process of convolution. And so I'm going to, for each relation on X, I'll define an operation on this thing. Using the ith relation, I make an operation fi. What do I do for these n functions? Well, I define them at X to be the convolution. This is exactly the way we did it before, a join of meets And this is taken over all x1 up to xn that are related to x in our relation. So what we did before is an instance of this. Now there's a bit of an arbitrary choice here, why a join of meets. We could equally well have done a meet of joins, and I'll call that the dual convolution operator. And the double convolution algebra, you just use both. Now, our type 2 fuzzy truth value algebra M is the convolution algebra, where the I on the bottom is the unit interval, that's complete lattice, and the I on the top is this relational structure. You know, join or supremum on the real unit interval is a ternary relation. It's a binary operation, it's a ternary relation. And so forth. With operations viewed as we have two ternary relations, a binary relation, and two unary relations. So that this is, so what have we done? We made a complicated definition based on another complicated definition of a type 2 fuzzy truth value algebra. This seems, maybe it's interesting, but it seems a bit, are these the only examples of this? Well, here. Let's make a little bit of a different story. Very related quickly though. Suppose I start with an ordinary group. I can view this thing as a relational structure with a ternary, binary, and unary relation. Its complex algebra of a group is the group complex is a collection of all subsets of the group where you define operations in this kind of way. How do you multiply two subsets of the group? You multiply all their elements together. That gives you a new subset of the group. How do you invert a subset of the group? You take the set of all elements, inverses of elements of the group, so forth. This group complex has been studied for a long time, apparently since Frobenius, so way back at the start of the subject. And these things are very logical structures. There's something known as a relation algebra. So these complex algebras are quite interesting, quite well-known things. And let's look at them another way. So for a relational structure X, its complex algebra is the power set of X with operations defined this way. F of a bunch of subsets is the set of all X such that there exists a tuple such as this in our relation where this is an X A1, this is, and so forth, and this is an AN. The dual complex algebra is achieved this way, and the double complex algebra this way. So this is one of the very basic key ideas of modal algebra in Kripke semantics. The idea of going from a relational structure to a, well, what do you get? You get a power set, a Boolean algebra with additional operations. This is the connection between this many world semantics and an algebraic treatment of modal logic. Okay. So this is an example. This is where you use complex algebras in logic. At least one of the places. Now there's a fundamental relationship. So I switched gears here. I went from convolution algebras to talking about these complex algebras. But of course, there's a very tight connection. Is that for a relational structure X, this is its complex algebra, is this convolution algebra. Convolution algebra where you choose the complete lattice 2. Right? 2 to the X is going to be the power set of X. And the way the operations work are exactly that way. The dual, and so forth. So the convolution algebra is a version of, one way to think about it is a version of a complex algebra that you can apply to lattices that are other than the two-element lattice used in classical logic. Now, here I won't prove this here. I'll just state it. You can get some nice, trivial complete lattice, meaning has more than one element. If L has one element, it's not very hard to figure things out. But the way I phrased the statement doesn't work. Is if L is a frame, meaning it's distributive and it's so I'm assuming it's complete, so I can form these things. Is a frame means that finite meets distribute over arbitrary joints. These are the things that these are sort of the analogs of topological spaces in lattice theory. So if L is a frame, this and this satisfy the same equations. So the theory of this thing is quite tractable. You can reduce it down to the theory of this thing, the equation theory. If L is a dual frame, then the dual convolution algebra and the dual complex algebra, or the dual complex algebra and the dual convolution algebra satisfy the same equations. And if this is annoying, I don't know why there's I don't know if I need to get this much more general here. It's a little bit of an open question here. If it more than just a frame and a dual frame, if it's completely distributive, then you get that the double convex, the double complex algebra and convolution algebra satisfy the same equation. And so this, remember way back at the start, I gave these, I said that the M satisfied the De Morgan equations for De Morgan algebra and these things and stuff like that. So how would you do this without making your life a misery? Well, it's quite easy. We're just dealing with a complex algebra, so our real unit interval is a frame. It's actually completely distributive, and so this is M. And this is the complex algebra, the regular complex algebra, the real unit interval. And it's quite easy to figure out the properties of the complex algebra of the unit interval. You're just talking about subsets of the unit interval. And so this is quite a simple way to get through there. Now, we can make this a bit categorical here. If you let lat be the category whose objects are complete lattices and whose morphisms are maps that preserve finite meet and arbitrary join. You do it slightly differently. Same objects except different maps. Same objects and arbitrary meets and arbitrary joins. So you've got some, basically you've got some categories of lattices. Make some category of relational structures of a given type. So you want to fix the number and the arities of the operations. And what do you use as morphisms? You use the usual logical definition of a p-morphism. I won't explain that here, but there's a well-known logical definition of a p-morphism between relational structures. And you make algebras. This is the category whose objects are complete lattices with additional operations. Then what you get is that this convolution process takes a complete lattice and a relational structure, and it gives you an algebra. This winds up being a bifunctor. And you can make nice properties about it preserving various kinds of things. And I won't go into that, but that's been studied and it works out quite nicely. Taking, what does it do to products and coproducts and things like this. So there's quite a nice theory of that works out very generally. So the interesting part is that the p-morphisms play very nicely with convolutions. That's essentially what this is saying. Now, get the little diagram down here. What would this be? So it takes an object. An object here is a pair, a lattice, and a relational structure. It takes takes that to this convolution algebra. And so we need, but a bifunctor has to preserve more morphisms as well. So you have a morphism from a morphism in here is a pair. It's a morphism between the lattices and a p-morphism. And so the other way around, it's a p-morphism. I think I've got a typo there, and it takes it to the natural thing there. So I've got one more direction that I'd like to go, and I tried to warn you at the start that I was going to make a little circuit, little tour through various things. So we've done a fair amount of a tour so far. We talked about fuzzy things, and we talked about convolution algebras and how they generalize complex algebras. So that was quite a shift of gears. And in this convolution algebra business, it had the fuzzy business as an example, although there are lots of others. Now we're going to bump up one level of abstraction here, and we're going to talk about top Y a little bit. So I'm not going to define what a topos is here. If you know, you know, and if you don't, it's impossible to do it in 5 minutes, but I'll give you a rough flavor of it. A topos is a type of category that has features similar to a category of sets. And each topos has an internal logic describing how things appear within the topos. And in sets, the internal logic is classical Boolean logic, but in a topos, it can be, in general, it's a hiding algebra, and you have an intuitionistic logic within a topos. Now, everything I'm going to say here is in a particular kind of topos called a topos of Étale spaces. And this has a more concrete realization, and I'll describe what this is. So an Étale space E over a topological space Y is the following things. It's a topological space E and a local homeomorphism from E to Y. So if you've ever worked with sheaves, you'll recognize this kind of thing. So a local homeomorphism means that for each point of E, there's a neighborhood around that point, with pi restricting to that neighborhood being a homeomorphism with the image. So here is one Étale space. The space E, you're given space Y, and the local homeomorphism. Here is another Étale space. Same Y. Y will be fixed all the time. Different E, E prime. So what's a morphism between Étales over Y is it's a continuous function between their display spaces that takes, you call this a stock, the stuff that's above a particular point. By above, I mean pi maps all these to here. It's the pre-image of Y under pi. Takes this stock to this stock. So this is the category of Étale spaces over Y. And this category is a topos. Not every topos is one of these, but this is a topos. The category of Étale spaces over a given Y, okay, I should have said that, is a topos. And it's objects. So one Étale over Y plays the role of a set. You can think of it as a continuously varying set. It's just words, but they're nice words. Okay? Just as ordinary sets have subsets, Étales have subobjects. in the usual categorical sense of a subobject. There's also an étal that plays the role of a power set of a set. It's the power étal of an étal. Anything you can do with sets, you can do with étals. Take the product of them, take the union of them, and so forth. They behave like sets. They are sets internally in the topos. Okay? Much more complicated than sets, right? But they are externally, they're more complicated. Internally, they're just sets. Okay? Now, in this case, the subobjects of an étal E are the open sets, at least correspond to the open sets of E, at least naturally considered as étals on their own. Okay? So you take an open set of E, and it's got a local homeomorphism down to Y. Okay? This doesn't have to be onto. For a set X, let the constant, an actual set X, let the constant étal over Y be this space. Take the product. Here, X has a discrete topology. Okay? Should have said that. So here's the product space. So if I take if I take this set, give it the discrete topology, take the product space, I get that. And what's the natural, the local homeomorphism is a natural projection. Okay? That's an étal space, very simple. That's a constant étal. Now, okay, we've really shifted gears. What does this have to do with type 2 fuzzy sets and convolution algebras? That's where we want to go in the time we've got left. So let's talk about type 2 fuzzy sets first. How can I make some link to the unit interval? Well, there's a little trick. I'm going to let Y be the topological space consisting of real unit interval without its right endpoint, with the half open intervals as the open sets of Y. So this is a perfectly good topological space. What does its lattice of open sets look like? Its lattice of open sets looks exactly like the real unit interval. The biggest open set is the whole thing, and otherwise we've got one for each lambda, and we don't have one for 0. Well, we have the empty set when lambda is 0. So the open sets of this topological space are exactly the real unit interval, and this is one part of where I make a tie to type 2 fuzzy sets. And there's a key observation by Ola. Fuzzy subsets of X, ordinary type 1 fuzzy subsets of X, correspond to subobjects of the constant étal given by X over this funny topological space. Now, what is a subobject of the constant étal? We said, so here's the constant étal. What's a subobject of this? It's an open subset of the top. Now, remember that it's the product topology on the top where X has the discrete topology. So it's really just given by a family of open subsets of Y. But the open subsets of Y are just basically correspond to real numbers. So a subobject of here is really just a function from X to 0, 1. So that's a type 1 fuzzy subset of X. So the subobjects. So that's how to view a that's how to view make the connection between regular fuzzy set theory and this topos theory. Now, as a little note, subobjects of the constant étal over the unit interval correspond to elements of our type 2 fuzzy truth value algebra M. Let's work a little bit more. And key to our discussion of convolution algebras was the starting point. One of the starting points was that of a relational structure. So a set with a family of relations. So an n-ary relation on a set X is just a subset of this. Now remember, anything that you can do with sets, you can do in a topos. An n-ary relation on an étal, E, is a subobject of the product étal. Internally in the topos, it's a relation. It's literally a relation in the topos. But this is the external view, is it's a subobject of the product étal. The internal view is it's a relation. A relational étal is an étal with a family of relations. And for a relational étal, I'll define its external complex algebra to be the set, the ordinary set of subobjects of E with operations given by relational image. And you get the theorem that our type 2 fuzzy truth value algebra M is isomorphic to this external complex algebra of the constant relational étal over I. Now, what we said was true for, we've been going back and forth a little bit between the specifics as applied to fuzzy sets and the general kind of theory that applies elsewhere. If I, instead of my funny topological space from the unit interval, if I take any topological space, Y, and let L be its frame of open subsets, so this is a complete lattice of open subsets, and I take any relational structure, then the convolution algebra, as we defined it before over this relational structure, it's always the external complex algebra of this constant relational étal. Now these are both external notions. So this is obtained looking at the topos from the outside. I mean, this has nothing to do with the topos. And this is all the actual set of all subsets, of all subobjects of a constant étal. There's a difference between an actual set and a set within the topos. Now a topos is like a set theory. We can make internal complex algebras in the topos as well. They're created via these things called power objects. And so the theorem is that this thing, L to the X, this is an external object. How do I relate it to an internal object? It's isomorphic to the algebra of global elements of the internal complex algebra of the constant étal. So this funny thing from the outside, these convolution operations, they come about just from this old Frobenius notion of a complex algebra, but applied in the very fancy setting of a topos of étals. The advantages, or an advantage is, well, conceptually there's an advantage, but also proofs that work in set theory work in toposes as well. So you can prove things about these things by applying a proof, by taking an existing proof about complex algebras that works in sets, and it applies equally in a topos. And so as a corollary, our type 2 fuzzy truth value algebra M, which seemed unusual, is isomorphic to the global elements of the internal complex algebra of this constant relational étal made from the real unit interval. Now, it's tempting to conclude that the type 2 fuzzy truth value algebra, there's still one external notion sitting in here. The external notion sitting in here is the unit interval. We're taking the constant relational étal from the unit interval. But this is the external unit interval. There's an internal unit interval in the étal as well. And it's not the same. It's not the same thing. So it's tempting to conclude that the type 2 fuzzy truth value algebra is the internal complex algebra of the real unit interval in the topos of étals over Y. Almost, but I is not the internal real unit interval in this topos. These issues will disappear if we modify the approach and replace the relational structure I with its rational counterpart. Then you do get the theorem you want, but you no longer have the actual real numbers. But if you're worried about the actual application of type 2 fuzzy sets, then who cares if it's the reals or the rational sitting down there. And I'm still how to put it, I think that Zadeh, I have a real appreciation for the insight that this guy had. I'm not a complete believer in fuzzy things. I've worked in them a little bit like other things, but I do just as a mathematician. It's the definition he gave based on very sketchy kind of things I find was a very insightful one, and that if you poke, you can find some real content in a lot of things. And so, thank you very much. Here's a little picture of Las Cruces. I hope you can all come visit sometime. So, thank you.
Thank you, John. It was very insightful. And thanks for the talk. Do we have any question for our speaker?
Can I ask something? You were mentioning the connection to the Tarski-Johnson papers on Boolean algebras with operators. Can one kind of interpret this in this topos theoretic formulation as a standard stone duality in a topos? Or this is maybe just a wild shot?
I hadn't thought of it. I hadn't thought of things in this way. I'd more thought of the thing that but you know, we all get these things that we intend to do at some time and never do. But the thing I'd intended to do was to see if you can lift the Janssen-Tarski ideas profitably up to an intuitionistic setting. That's the idea I thought. I hadn't thought of recasting. I hadn't thought of it this way, but I would add that to it. I hadn't gone through that thought process.
Any other question? So I probably don't, I mean, I never studied fuzzy set theory before. You did mention that some people believe in fuzzy set theory and others do not. Can you sort of like describe a little bit? Because I believe many among our audience do not have this kind of understanding either.
Yeah, I mean, how to put things. I've worked in a couple of different areas, and one of them is quantum logic, and I've probably done more in quantum logic than in fuzzy sets. I've just worked a little bit with fuzzy sets. My attitude is there are different streams of thought. Is that in quantum logic, you can view this as an actual, you can take the path of saying, I want to view this as an actual logical system. And in some sense, there are different ways to define an actual logical system or something like that, but you can take it very seriously in that vein. And it may have good, I'm not going to argue for or against that. You may run into problems and say, it's not actually an algebraizable logic in the sense of, Bloch and Pagozzi or some other kind of thing, and you can take it very seriously like that. That's never been my thing. Quantum mechanics exists, and you use tools that are similar to logical tools in studying it. So I don't care whether it's actual, well, I shouldn't say I don't care, but it's not my primary motivation whether it's an actual logic. I want to study the thing. The thing exists, and these logical tools are of interest. And you can, and many people are quite expert in whether it is an actual logic or how you can do it or not. And that's never been my motivation. And similarly with fuzzy things, you can have very technically loaded words such as belief functions and things like that, and things, and you can say, is this an actual logical system we're dealing with here? And they're fine questions. But for me, there is no doubt that fuzzy sets exist. I mean, things in our homes are built using them. There is no doubt that these things exist, and they are useful. If you have a camera, it may use that. If you have a little helicopter flying, helicopters fly with this, don't fly without. It exists, and it's interesting. And to study it, you can profitably use logical tools. And that's what I would like to do. And so I'm completely agnostic about the question of, is it a logic and things like that, because it's not my motivation, right? And I'm not an expert on it. And so when I say these words, I just don't want to offend people who are on one side or the other, because it's irrelevant to me in the context that I'm speaking. Does that make sense?
Yeah. Yes, thank you. One last question. Okay, looks like we don't have any question. So thank you once again, Professor Harding, and thanks for the nice picture. Perhaps one day we will visit New Mexico. That's right.
Yeah.
Right. Okay. Thank you, everyone. That is the end of the session for today. I hope to see you again tomorrow. So you can check out the schedule at the conference homepage. Okay, we'll have 4 more talks tomorrow. Thank you, everyone. See you tomorrow.